In this lesson, we're going to continue on with our look at probability and deal with the rules for the probabilities of and, or, and not. Two terms that will come up as we go through this are the ideas of independent and mutually exclusive. Now, we looked at independent in our last lesson, and we learned that there is a test for independence, comparing the probability of A given B to the probability of A. Now, another way of saying what we actually did mathematically there is that two events are independent if the probability of the one is unaffected by whether the other thing has happened or not. So if the outcome of one event does affect the outcome of the next, then those events are not independent. Mutually exclusive is something else. If we're dealing with mutual exclusivity, what we're talking about is whether two events can happen at the same time or not. So two events that are mutually exclusive cannot happen at the same time. If they are not mutually exclusive, then they can happen at the same time. So let's look at our rule for and to begin with. If we're to look at the probability of a randomly selected customer being satisfied and male, when we're talking about and, we want to think about that idea of mutual exclusivity. So can these two events happen at the same time? Well, yes, it is quite possible that we could have a customer that is not only satisfied, but they're also male. So we look at instances where both those things happen at the same time. So not only are we not concerned with any of the females, but we're also concerned with anybody who is not satisfied. And here what we find is that 4 out of our 11 clients are not only satisfied, but they are also male. And relating that in its decimal form, we would get the probability of satisfied and male is 0.3636. This is an example of a joint probability. If we were to look at two events that are mutually exclusive, so we ask, what is the probability of being satisfied and not satisfied? So those events are mutually exclusive. They cannot happen at the same time. And if we do the joint probability of that, there is no junction point of those two things. There is no overlap between not satisfied and satisfied. So the joint probability of two mutually exclusive events will always be 0. We could have also done this example with either our contingency table or, in the case we have here, our joint probability table. If we look on this table, what symbolizes not only being satisfied, but being male as well? So not only are we talking about being satisfied or being male, we need both those things to happen. So we're looking at the junction point or the joint probability. So where those two things occur at the same time, we have the joint probability or the junction point of those two things of 0.3636. So we can tell those events are not mutually exclusive because there is an overlap between both of them. They can happen at the same time. If we were to, again, from this table, look at the probability of being satisfied and not satisfied, well, what we would see is there is no junction point between those two. The satisfied column in no way overlaps with the not satisfied column. And again, because there is no junction point there, the probability of two mutually exclusive events will always be 0. Looking at the difference between joint and conditional probabilities. So remember from what we just looked at, talking about a joint probability, we're looking for that junction point. We're looking for and. With conditional probabilities, we're looking for one event given that something else has already happened. We can symbolize the joint with our and symbol, the ampersand. Given is symbolized with that vertical line. And the big difference between these two things is that when we're talking about a joint probability, we're looking at that probability compared to the entire sample space. With a conditional probability, we have limited that sample space to, in this case, we're only looking at the male customers. We've looked at and probabilities in terms of a single event and whether that is mutually exclusive or not mutually exclusive. Well, let's look at now compared to multiple events and whether we're dealing with two events that are independent or not independent? When we're dealing with and multiple events, we want to think about multiplication. If the events are independent, then we simply multiply those two probabilities together. The probability of event A times the probability of event B. So a couple examples. Here we have a company launching 2 new CDs, one for a country singer and one for an opera singer. We have the probability that the opera CD is a hit is 0.07. The probability of the country CD being a hit is 0.03. What we're asked to find is the probability that both are hits. So really we're asked to find what is the probability that the opera is a hit and the probability that the country is a hit. We have to think about, are these events independent or not independent? Well, if we think about, is there any way that the opera one being a hit has an effect on the country one being a hit? I would have to think no, which means since there is no effect from one on the other, the events are independent. And with the events being independent, we can simply multiply the probability of an opera hit times the probability of a country hit, giving us the probability of an opera hit and a country hit being 0.0021. Sometimes you may see these probabilities being represented in what is known as a tree diagram. So here we're told that 2 events are independent, and the probability of being female is 0.3, the probability of a pass is 0.9. We're asked to fill in the tree diagram and calculate all of the joint probabilities. So what we know so far is that we have a probability of 0.3 of being female. Well, what would that mean in terms of the probability of being a male? Now this will actually take us into what we'll look at a little later in this lesson, the idea of not. Well, if the probability of being a female is 0.3, then the probability of being a male is 0.7. We were told that the probability of a pass is 0.9, which would mean the probability of failing would be 0.1. And the fact that it told us that gender and course success were independent right off the bat is very important, because what does that mean? It means that it doesn't matter if I'm talking about the males or females. It means the probability of passing and failing is the same regardless. So passing for males is also 0.9 and failing for males is also a probability of 0.1. If we want to now calculate the joint probabilities, first looking at the probability of being female and passing, since the events are independent, we can simply multiply them. 0.3 times 0.9 gives us a probability of being female and passing is 0.27. The probability of being female and failing would be 0.3 times 0.1, giving us 0.03. And similarly for the male, multiplying those respective probabilities, we get male and passing at 0.63 and male and failing at 0.07. One quick check we can do to make sure that we did all those joint probabilities correctly is if we total up all of our joint probabilities, they should bring us right back to all the possible outcomes of this experiment, which means that we should be right back to 100%, or a probability of 1.0. So if we total up 0.27 plus 0.03 plus 0.63 plus 0.07, we are right back at our total probability of 1.0. So that was dealing with independent events. Dealing with not independent events, and remember what we mean by not independent is that the one event has had an effect on the second event. We're still thinking about multiplication, but now we have to take into consideration the probability of A, not just times probability of B now, but the probability of B given that event A already happened. Now, just speaking in words, that may sound quite confusing, but let's look at an example, and hopefully it can clear up a bit of that confusion. Here we're dealing with people applying for a job. We have 10 female applicants and 12 male applicants. The hiring company has randomly selected 2 people to interview. What is the probability of that random selection that both of those people are male? Well, we have to think about, does the fact that the first person getting interviewed, being male, have an effect that the second person being interviewed is male? To do this, let's take a look at our entire sample space, so 10 female applicants and 12 male applicants. So here is every possible applicant we're talking about, our 10 females, our 12 males, giving us a total of 22 applicants. So if I look at the probability that the first applicant is male, and I take him out of my applicant pool, what is the probability that that first individual was male? Well, in our pool we had 12 males and 22 total applicants. So the probability that I select that first individual and that they're male is 12 out of 22. Now we have to think about, does that individual get placed back into the pool? So the issue of replacement is very important here. If I was to put him back in the pool and select again, well then the next applicant would also be a probability of being male of 12 in 22. But they're not going to put him back into the pool and interview the same person twice in a row. That wouldn't make any sense. So here he's not being replaced. And if I think about how that affected my sample space, well, now there's one less person to choose from. There's only 21 applicants left to choose from. And there's one less male to choose from, which means the probability that this second individual is a male, yes, there has been an effect on him. His probability is no longer 12 and 22, but his probability is now 11 males left and 21 applicants left. The probability of getting that second individual being male is now 11 out of 21. So going back to our question, does the chance of the first interviewee being male affect the chance that the second interviewee is male? Yes, it does. So because the one event affects the other event, those two events are dependent or not independent. So now when we're doing our probabilities, we have to look at the probability that we get the first one male times the probability the second one is male, given that we already had that first one as a male. So again, in words it may be a little muddy, but all we're really doing here is we got the probability of the first one being male. That was 12 and 22. And we saw that the second one, his sample space was affected, and the probability of the second one being male was no longer 12 and 22, but it was now 11 and 21. All we have to do is take into consideration that the first applicant pick was male, and that did affect our sample space. So now, dealing with and, we deal with multiplication. Probability the first is male is 12 and 22. Second one being picked, our sample space went down a little, our male applicants went down a little, so we multiply that by the probability of 11 over 21, which means, to 4 decimal places, the probability that the first is male and that the second is male is 0.2857. Now when we see the term or, we're no longer thinking about multiplication, we're thinking about addition. And what we have to ask ourselves now is, are the events mutually exclusive or not mutually exclusive? So can they happen at the same time or can they not happen at the same time? If the events are mutually exclusive, which remember means they cannot happen at the same time, to do the probability of A or B is simply adding their two individual probabilities. So if I'm to go back to Dr. Miller and look at the income levels of his clientele, and we were to be looking for the probability that a randomly selected customer has an income below $25,000 or above $75,000, well, first thing we ask ourselves, are those two events mutually exclusive or not? So can somebody have an income under $25,000 while at the same time having an income over $75,000? No, they cannot. Therefore, the events are mutually exclusive, in which case we simply add their two individual probabilities. So the probability of having an income under $25,000 is 29 out of 546. The probability of having an income over $75,000 was 12 out of 546. So adding those two probabilities together, we get that the probability of under 25,000 or over 75,000 is approximately 0.0751. If we're to look at in this example, what is the probability that a randomly selected customer is satisfied or male? So satisfied or male, the probability of being satisfied, we see is 8 and 11. The probability of being male is 6 and 11. If we're to add those two probabilities together, we get that the probability of being satisfied or male is 14 and 11. Well, right away, you should be thinking that there's something pretty fishy going on here. The absolute highest probability we can possibly have is 100%, or a probability of 1.0. Here we have a probability of greater than 1. So something is definitely off. The probability is not 14 and 11. If we think to ourselves, what did we forget to do? Well, we forgot to ask ourselves, can these two things happen at the same time? And here they can. You can have somebody that is not only male, but at the same time they are male and they are satisfied. And if we look at what we did when we added the probability of satisfied plus the probability of male, everybody that was satisfied and at the same time male was counted twice. So we want to make sure we count those people, but we definitely do not want to count them twice. So what we need to do is get rid of one of the instances where they are both satisfied and male. So if we subtract one of those sets of 4 of the 11, then we will only have counted those individuals that are satisfied and male one time, in which case we get our appropriate probability of 10 out of the 11 customers are either satisfied or they're male, giving us a probability of 0.9091. And if we go back to our entire sample space, we see that in fact there is only one client who is neither male nor satisfied, and that is the one individual that is female and not satisfied. So looking at our rule, if we do have events that are not mutually exclusive, so remember not mutually exclusive means they can happen at the same time, the probability of A or B, yes, we have the probability of A plus the probability of B, but we have to make sure we get rid of one of those instances where we had both events occur at the same time. So we subtract one instance of the probability of A and B. We'll go now and do the exact same question we just did, however within a joint probability table. And again, dealing with OR probabilities, we have to ask ourselves, can these two things happen at the same time? Well, what we should see is that yes, they can, because there is an intersection of those two things. So not only do we add the probability of being satisfied, 0.723, plus the probability of being male, 0.5455, but we have to get rid of one of those instances where they happen together, which is the intersection between those two things, so minus the probability of 0.3636, giving us a probability of 0.9092. And again, we have a slight discrepancy between our value here and when we calculated the probability looking at the actual sample. And the reason for that discrepancy is because of the rounded values that we've used in this table. Looking now at something called the complement rule, if we're to look at our sample and ask ourselves what is the probability of selecting a male, well, 6 individuals from our 11-person sample space are male, so we have a probability of 0.5455. If we were on the other hand to ask ourselves what is the probability of not selecting a male, well, we see everyone that wasn't in our first sample, wasn't in our male sample, would be not a male. So what's left over there is 5 out of our 11 customers were not male, or a probability of 0.4545. Or if we're to look at that another way, 1 minus the probability of a male, so 1 minus 0.5455, gives us a probability of 0.4545, which is the same as a probability of not male. Or another way of rewording it, so complement event, everything in a sample space that is not the event that we're talking about. And now you may see the complement of an event symbolized different ways in different textbooks. However, our textbook uses the superscript C. So what we're looking at here is the probability of the complement of event A is simply 1 minus the probability of A. And as we said, we had already seen that a couple times in this lesson. We saw the probability of not male that we just did. Or back when we were creating our tree diagram, we were given the probability of female, and using 1 minus the probability of female, we found out the probability of our males. Or we were given the probability of passing, and from that, we did 1 minus to find us our probability of failing. So as a little recap, we talked about mutual exclusivity and independence. With mutually exclusive events, we had to ask ourselves, can both events happen at the same time? If the answer was no, then the events were mutually exclusive. If the answer was yes, then the events were not mutually exclusive. They could happen at the same time. Now, looking at how that affected our probabilities for or and, if we had mutually exclusive events, remember when we're talking about or, we're thinking about addition. So if they can't happen at the same time, we simply add the probability of event A and event B. If they could happen at the same time, we ended up with that little bit of overlap. So we were counting too much stuff. So we had to count the probability of A plus the probability of B and subtract off one of those overlapped incidences. When we were talking about and, for mutually exclusive events, two events that cannot happen at the same time, the probability will always be 0. If they are not mutually exclusive, so they can happen at the same time, and is simply the junction of those two events. Dealing with whether events are independent or not, we ask ourselves, does the chance of the one event happening affect the other event? If we answer no, then the events are independent. There is no effect from the one on the other. If we answer yes, then they are not independent. And how that affects our probability is we were dealing with and remember with and we think about multiplication. So if there was no effect from one event on the other event, therefore they are independent, we can simply multiply the two probabilities, the probability of A times the probability of B. If they were not independent, the one event did affect the other, we had to now multiply the probability of event A happening, but then take into consideration for that probability of B that A had already happened. So we have that reduced sample space in our probability of B. What I would ask you to do is to pause the video here and attempt this problem. So for question 1, we were asked, what is the probability that a customer is an adult and purchases popcorn? So remember, the first thing we want to do anytime we have a contingency table is to first calculate our totals. So now that that is done, all our totals are calculated. Looking for the probability of adult and popcorn, well, that would occur at the intersection between our adults and our popcorn. And where those two things intersect, we have a frequency of 336. Therefore, to get the probability, we take our frequency 336, divide it by our total of 1,944, and we should get that the probability of adult and popcorn being approximately 0.1728. In part 2, we were asked what the probability that a customer is a senior or does not purchase popcorn. So when we're talking about or, we are thinking about addition, and we have to think, are these events mutually exclusive or not? So can they happen at the same time? Is there an intersection point? And if we look at our seniors, we have 378 of them. No popcorn, 1,080 that didn't purchase popcorn. We do have an intersection point here, 210 people who are both senior and no popcorn. So we have to subtract one of those instances off, as we've included those 210 people in our seniors and in our no popcorn. So subtracting one of those instances off, what we should get, the probability of senior or no popcorn, is 0.6420. In question 3, when it asks us, is customer type related to popcorn purchasing? What we need to do here is our independence test. So in terms of the independence test, it doesn't really matter what we check for events A and B. The one thing we make sure of is that our single probability A is the same thing as the first part of our conditional probability. So the single probability A against the conditional probability A given B. And what we consider as event A, whether we say that to be child, adult, or senior, or for that matter popcorn or no popcorn, the only thing we need to make sure for event B is that if we called A to be one of our top row values, child, adult, or senior, event B has to be popcorn or no popcorn. If we considered event A to be popcorn or no popcorn, then event B has to be one from our top row, child, adult, or senior. I'm going to consider the single event of the probability of a child, and the probability of that event is 810 over 1944, or 0.4167. So now that I've considered event A to be a child, I need to check the probability of a child either given popcorn or the probability of a child given no popcorn. So if I check the probability of child given popcorn, as soon as we put that condition on it, now we don't care about anything other than that popcorn row. So from that popcorn row, we see there were 360 children out of the 864 that purchased popcorn. So we had a probability for event C being 0.4167. We had the probability for event C given P of being 0.4167. And since those two things are equal, remember they're equal, they pass the independence test, which means they are independent. If they are independent, they are not related. So what this means is those two events are not related, in which case, whatever age group you're in, child, adult, or senior, all of them are equally likely to purchase popcorn. So again here I would like to ask you to please pause the video and attempt the problem on your own before proceeding with the actual solution. Looking at part A from this video, what is the probability of selecting all females? So in this case, we're looking at the probability of getting a female first, and a female second, and a female third. Talking about and, we have to think about two things. First, and refers to multiplication. Second, are these events independent or not? Does picking a female first affect the chance of picking a female second? And without replacement, yes it does. So here, our events are not independent. So what we need to think about is, what is the probability of getting a female first? Well, the probability of the first female is there are 8 of them in our sample space of 18 individuals. Well, now that we have one female gone and one individual gone from our sample space, the probability of the next female is now there are only 7 females left and 17 people in the sample space. For the third person, well, now there are only 6 females left and 16 people in the sample space. So we have the probability of 8 over 18 times the probability of 7 over 17 times the probability of 6 over 16 giving us the probability of getting all three to be female is 0.0686. In part B, we're asked what the probability of selecting one male and two females is. So what we have to think about here is when we dealt with the first part of this question, there was only one way that I could get three females. I had to get a female first, a female second, and a female third. Here, there are actually multiple different ways to get one male and two females. I may get the male first, the female second, and the female third. Or I could just have likely got the female first, the male second, and the female third. Or one last way, I could have got a female first, a female second, and the male as my third pick. Now, when calculating this probability, I have to consider each of those events. Probability of the male, female, female, or the probability of the female, male, female, or the probability of the female, female, male. Now, calculating any of those individual probabilities, male, female, 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 male, female, 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 male, what you should find is that those will all give you the same probability. It doesn't matter if we do 10 times 8 times 7, or 8 times 10 times 7, or 8 times 7 times 10. Order of multiplication doesn't matter. 2 times 3 is the same thing as 3 times 2. So each of those will give me a probability of 0.114 and all the other decimals associated with it. So as long as we can calculate one way, and we know that it happens three different ways, we simply take the calculation from one of those ways and multiply it by 3. So anytime we have multiple different ways of getting to that same outcome, if you know there are 6 different ways you can get to that outcome, calculate one way to do it and then multiply that probability by 6. Here, all we needed to do was, because we knew we could get it 3 different ways, calculate the first way, multiply it by 3, and we get the probability of selecting exactly one male and 2 females is 0.3431. Last but not least, what is the probability of selecting at least one male? Well, if we're talking about at least one male, well, we could be talking about getting exactly one male, and we found that there's 3 different ways to do that. We could also be talking about getting exactly 2 males, which there's also 3 different ways to do that. Or we could be talking about getting all males. So to calculate this properly, we would have to calculate each of those individually. Calculate the probability of one male. Multiply it by 3 because there's 3 different ways that can happen. Calculate the probability of 2 males. Multiply it by 3 because there's 3 different ways that can happen. Calculate the probability of getting all 3 males. And then add all those probabilities together. That is a lot of calculations. And there actually is a trick. Anytime you see that term at least one, what should jump into your mind immediately is that complement rule. The reason the complement rule is very beneficial when we talk about at least one is because the only way I'm not getting at least one is if we get all females. So in very non-statistical terms, what the complement rule is saying is that if we do 1 minus what we don't want, we're going to get the probability of what we do want. Well, what we don't want is to get 0 males. Well, 0 males would mean all females. And we've actually done that calculation already. If we hadn't done that calculation in part A, we would have to go and do the calculation for getting 0 males or getting all 3 females. But we saw in part A that that probability is 0.0686. which means the probability of getting at least one male is 0.9314. You should get exactly the same answer if you take the time to figure out the probability of getting one male, plus a probability of getting two males, plus a probability of getting all three males. Add all those together, you should get that exact same value.